Welcome everybody to Advancements in Aerospace. This is STEM Lyceums, and we're so happy to have all of you. Before we introduce our fabulous speaker today, we are going to do just a quick overview of CEE and all the amazing stuff and things that we do. So first, as many of you know, the Center for Excellence in Education, it was founded in 1983 by Joanne DeGennaro and the late Admiral H.D. Rickover, who was the father of the nuclear navy and civilian uses of nuclear power. The mission at CEE is to nurture high school and university scholars to careers of excellence and leadership in science, technology, engineering, and mathematics, or STEM, and to encourage international collaboration between and among leaders in the global community. At CEE, we have 4 amazing programs, first of which is RSI, the Research Science Institute. RSI is a highly competitive 6-week summer and science engineering program open to rising high school seniors. Juniors are eligible to apply. RSI is the first cost-free summer science and engineering program that combines on-campus coursework in scientific theory with off-campus work in science and technology research. Next, we have the USA Biolympiad, or USABO, the premier U.S. biology education and testing program for high school students. It provides the motivation, curricular resources, and skills training to take them beyond their classroom experience to the level of international competitiveness. Since CEE began administering the USABO in 2003, every member of the USA Biolympiad team has medaled at the IBO. Next, we have the Teacher Enrichment Program, or TEP. TEP provides opportunities for middle and high school teachers to connect with leading experts from industry and academia, explore cutting-edge research and development, and make meaningful professional links with direct benefits for teachers and students. Finally, we're here, STEM Lyceums, a virtual club for high school students to meet once a month to learn about STEM career pathways from leading field experts. Industry professionals share cutting-edge research and offer unique learning experiences like scholarships and internship opportunities for high achievers. If you want to learn more about our programs, please visit www.cee.org. And now I have the pleasure of introducing our speaker. So today we will be hearing from Dr. Jacob Temme. Dr. Temme holds a PhD in aerospace engineering and is a leading expert in combustion and aerospace propulsion. His research interests include using high-speed video and laser-based optical methods to understand liquid spray physics, turbulent flows, and combustion dynamics. He has over 18 years of experience in the field conducting fundamental research and applying it to advance new technologies. He currently leads research efforts at the U.S. Army DEVCOM Army Research Laboratory to produce energy and power solutions for the future. Dr. Temme, I'll turn it over to you. We'll stop sharing and we're ready for your amazing presentation.
Excited to share with you today some things about my work and kind of what led me to science here. As you already heard, right, there's a wide range of things that CEE does, but really where I got hooked into research originally was at RSI. And then from there, it just kept snowballing into the career and path that I'm at now. So definitely as you get experience, you're in one of CEE's programs now, check out RSI, check out other things. But if those aren't options for you, don't discount looking around your local college, right? It's not just some of the famous names you hear. It's not only MIT does research, or not only Caltech or Georgia Tech or Michigan or someone. All these local colleges have different research programs going on, and all of them have a research opportunity. You can search that. You can search the local professors. For most of us, call us up. We're happy to talk about our work, right? And in general rules, every scientist I know is happy to, if you want to know more about the science they're doing. The third bullet on there is the government lab system. Again, so things like Department of Energy, Department of Defense, there are government labs out there. We'll talk a little bit more about that at the end of the slide deck today, the opportunities with the Army Research Lab. But they also have a wealth of different opportunities to join and collaborate. So looking at my pathway and kind of how I got into science and these things, I started at RSI on this box here. So really trying to ask the question about satellites and how do we keep them pointing the right way, right? Any satellite you put into orbit is going to have some amount of orbital decay. So things like the space station in low Earth orbit, it's in space, but there's still tiny fractions of the atmosphere that are creating drag. And how do you keep it in the right spot? How do you keep it going the right speed? Or if you have a satellite and you want to task it to a new task, right? Right now we have chemical propulsion thrusters. We've got to take up some amount of fuel essentially. And when you run out of it, what are you going to do? For things that are small satellites, it's not really feasible to go up and refuel them. So at that point, you just let the satellite, it's the end of its life, and it crashes back into the atmosphere and burns up and makes a nice, pretty meteor shower. So one of the questions that the lab there was asking was, can we use magnets instead, right? Magnetic force doesn't run out. The magnet's always magnetic. So if I have two magnets, and you can try this at home, on your desk, put one magnet down, put another magnet down. If you spin or twist the first magnet, the other one will rotate to align itself with that. So the question becomes then, how strong can you make that effect? How strong can we make that effect while it's also lightweight? When we put things into space, right, the dollars per pound of things going up into space is very critical. So it was my first opportunity to kind of design an experiment, a hands-on, go build a magnet. You can have magnetic material, right? That's just a solid, or you could do electric magnets, right? If I build a coil of wires and put electricity through it, I can make electromagnets. So what kind of electromagnet could you design? Hopefully it should be lighter weight than a permanent magnet. And then, what would that shape look like to make the most amount of magnetic force across the longest distance? Can you have these things more than just on the same desk in front of you, a couple feet apart? Can you make these hundreds of feet apart or miles apart? How far could you push this effect? And so went into the lab, tried it out, built a few things, and it was my first experience with what in science we call a null result. It didn't work. You could get an effect, right? But it was never going to be strong enough. It was never going to be lightweight enough. And we also ran into a lot of thermal challenges. Things got really, really hot. And so it was a null result, it didn't work. But then I learned about every null result gives you a whole new array of questions to go after. Why didn't it work? Can I make that effect any better? The thermal things, is there new materials we could discover to help this now go from not working to work? And so that was a really great experience. It taught me a couple things that I like hands-on. I like building experiments, going into a lab and touching something, measuring something. It wasn't fully the thing for me, so I kept going. Next time, came back another summer. I'd gotten on a summer project. In the upper right here, looking at when you drop an object into water, is there a big splash or is there not a splash, right? What's the physics that controls that reaction? And so if you want to do things like you want to monitor fish populations or whales, and you don't want them spooked off by the object you're dropping on, or if you want to, in certain manufacturing, if you need to put coatings on things and you want it to be evenly coated, you want that smooth entry. And so is starting to understand, how do you get that cavitation? Is my introduction to fluids. In a lot of the field of fluids, we try and do things in non-dimensional parameters, right? So how do I generalize my experiments, not just from this one thing I studied, this one steel ball in water, but can I make it also work for a different liquid like oil? Can I make it work for something in a different shape, in a different form factor? Does it matter if the ball's coming in at an angle, how fast the ball's coming in? And so how do you generalize your results, right? It also taught me a lot about high-speed imaging and fluids. And so just trying to get out regime diagrams for kind of different combinations of factors and how you could reduce those to generalized properties that would give you kind of this either on-off behavior. And so I learned a few things, about what I liked and didn't like. And then that led me to the next experience. Started as a summer project, and then I continued it on throughout the rest of that year in undergrad. And kind of looking at manufacturing. So when we invent a new material, oftentimes, someone in the lab comes up with this new, crazy, amazing material, but then you don't know how to actually build things out of it. Because if it's super, super hard, well, that also usually means it's super, super hard to cut. Or maybe it's, different properties have effects on how you would actually machine and build useful things out of that material. So one of the things we were looking at with this lab was when you've got these new super hard materials and you go to cut them, you actually have a lot of friction on the tool tip and it destroys your tools. And so you've got to stop the manufacturing process, replace the tool, go in. There's a lot of cost there. There's a lot of downtime. And so the people are looking at how do you reduce that effect, right? So right now, as that cutting tool is scraping the surface of an object, you put some oil bases in there as a lubricant, right? To make things less friction. And so then you have less heating, less tool wear. But there's a lot of issues with that, right? Now you've got oil, leftover oil. You have oil that aerosolizes, and there's a lot of bacteria that wants to eat that. And so you get these weird biomasses that are growing. It's a health hazard for your manufacturing, your workers. There's also oil that's left over and that now has metal chips in it. That's a huge hazardous waste you've got to dispose of. So the professor there had this idea where could we do it a different way? And it combined two aspects. One would be replacing some of these heavy hydrocarbon oils with renewable vegetable oils, things that like soybean oil or rapeseed oil that you could use, and it was a lot more environmentally friendly. So you didn't have the hazardous waste component or as bad of one. And then also, could we replace and kind of deal with the heat? And how are we going to do that, right? And so this idea of supercritical fluids. So you're probably familiar with in your science class, solids, liquids, and gases in a phase diagram, how you heat something up or you pressurize it, you can go from a solid to a liquid to a gas. But then above a certain critical point, right, it becomes a supercritical fluid. It's not fully a liquid, it's not fully a gas. It's kind of this new phenomenon up there. There's not really interfaces between a liquid droplet. So when we put these liquid droplets of oil into the CO2 and I push past that boundary, there is no liquid gas boundary anymore. They completely absorb into that fluid. And so it's really good at then helping us put the oil into this mixture. But then the other really useful thing about that is if you take a supercritical fluid and you rapidly expand it out of a nozzle, you spray it onto the part, it gets really, really cold. In fact, it gets so cold if we use CO2, we actually form dry ice on the tooltip. And so you can do a lot of heat removal from all this high friction point on cutting these new exotic materials. And you can really extend the tool life and let you cut these really difficult things. So it was a great experience. It was a slightly different form, but I learned a lot about high pressure plumbing, high pressure systems, and a lot about computer image processing, which we'll get into a little bit more on the next slide too. But so much of science, and because we're visual creatures, we take visual measurements, but then we need to reduce those to actual quantifiable metrics. So where that really all led is I took more coursework and learned more about science and engineering and where I thought I could make a mark. I ended up getting advanced degrees from University of Michigan. And I went into a field where I'm firing lasers, right? So I light things on fire and I shoot them with lasers to understand how they work. And what does that really mean? Looking here, I started work kind of in this upper right-hand corner. So if you imagine you've ever flown on a jet engine, if we take that jet engine apart, there's some fan blades in the front, there's some fan blades in the back, and in between them is a small section. It's a toroidal shape. It looks like a donut, right? And around that torus, there are, say, 10 or 15 or 20 different, they look like shower nozzles, fuel injectors that spray out a little cone of fuel into that torus. And so to do science and understanding of all the different physics and chemistry that's in that process, what we needed to create was a way to get cameras in there. And so we take a section and we just kind of cut out one fuel injector that would stick through this hole on the back plate. And then we replicate what would be the outer walls of that torus as these upper and lower surfaces, and we put windows in there. And then the left, right, which would just kind of be open space if we were revolve this 360 degrees, but we put in some windows there just to contain the flame and again have optical access for all our different methods. And so this would be our vessel for researching how does the combustion work? What are combustion instabilities, right? When you're flying that jet engine, obviously none of us want it to turn off and stop providing power to the aircraft. That's generally a bad thing in aerospace engineering. So what do we do? How do we understand what creates those instabilities? How do we understand how the liquid droplets enter this chamber, evaporate, ignite, and burn and produce power? And so a picture of how this looks like when the flame's turned on is here right below that. Again, so I'm shooting left to right. You can see a couple key features of modern aircraft. So I've got kind of this big yellow flame in the middle, surrounded by a lighter blue flame. So I've got an inner pilot. It's a very rich, I've got more fuel than I need there. And so it's always stable. It's very hard to blow that out. And then around that, I've got the main flame coming in kind of in a leaner condition. I'm trying to reduce, improve efficiencies, reduce pollutants in the civilian side. And then you can also kind of see here at the end, there's this kind of swirling tornado effect going on. And so the design and the walls and the space and the entry air is designed such that I get that spinning effect. And what's that really doing? Well, this kind of in and the out page spinning is also working to do a spinning motion this way, up and downstream, to take hot products, hot gas from after the combustion flame, bring it back into the middle of this to heat up and help vaporize those fuel droplets and make this even more stable. The two kind of spinning motions create this flow pattern that really help lead us towards this technology working. And so investigated this, did a couple different optical type diagnostics. So in this set of images here, what we were looking at was just that instability mode. Depending on certain combinations of how much fuel you're putting in, what temperatures and pressures you were at, you could get this where you got kind of the flame base extinguished and the whole thing went downstream and became a flat pancake and then flashed back and reattached. And so you'd have this thumping mode of the flame in your combustor, which could eventually lead to the whole thing going out. And so kind of trying to understand the physics of why that happened, what initiated it, how could we control it, how could we avoid it in a real engine design. And so just a high-speed video of that. We also paired that with this image in the middle area referenced. Well, this is the actual velocity. So we can measure the velocity of the air. How do we do that? We take really tiny droplets of dust. So aluminum oxides or titanium dioxides. And if they're small enough, you can actually work out the math that they're small enough, they follow the fast motions of the air. If I spray a lot of these dust particles in the air and then I hit them with a laser beam, that laser beam reflects off of the dust particle back to my camera very bright. And it can be even brighter than this background yellow of the combustion. And so I can take pictures of that, sequential pictures of those reflected light from the dust particles, and I can track where the dust particles move between each picture. And so then I can calculate the speed and the local velocity of the air at that point and reconstruct what is the physics of the flow of the air motion as it goes through the flame. And I pair that with some chemistry information, right? So combustion is a lot of the interaction between that fluid physics and the chemistry. So a couple different ways I can measure chemistry in the flame, but one of the ways I did a lot of was called laser-induced fluorescence. And at its heart, fluorescence is really just the same thing as like when you take a black light. If you've ever gone in there and your white T-shirt or white things, your white business card will glow in a black light situation. Well, what's that happening? That's the UV light interacting with the residue of the soap that made that shirt white, and the phosphors in that soap fluorescing at a higher wavelength that's visible to your eyes. So UV light goes in and something like a blue or a yellow or a green comes back out. And so we can use that very carefully with laser beams. If I tune the laser wavelength to a very specific transition on a molecule, then it will fluoresce back at a different wavelength that I can put a very narrow pass filter on my camera and capture that information. So I can probe things like a formaldehyde molecule. And formaldehyde is a natural forming, very short-lived molecule as I break down fuel and start to enter into a flame reaction. So I can use that as a marker for where is chemical reactions and fuel breakdown happening. I can also do things like OH molecules, which are formed just after the flame. And so I can look at the post-flame behavior. And that lets me build up statistics of where exactly does the flame live, like this middle picture here. And so if I have pictures of where does the flame live with pictures of where is the velocity and what's the flow doing at that moment, capturing these kinds of informations with that instability mode gives me that full understanding of how all these processes are going together and how I can improve the performance of a jet engine. So this was a kind of a very applied research, right? I was asking fundamental questions, but I was applying them towards a very practical output for my thesis. So my wife and I, we stuck around Michigan a little bit longer. I did a postdoc there and kind of switched it up, went back to a very basic fundamental theory kind of problem. So going back to what we mentioned on the cavitation, the dropping balls in water, a lot of fluid dynamics is kind of developing regime diagrams. So if we can match conditions where different phenomena tend to occur, and then there seems to be a boundary, a naturally occurring boundary before a different kind of phenomenon occurs. And so one of those that we look at in flames is where we have kind of very thin regulated flames or wrinkled flames or flames that are starting to tear apart. And there are different theoretical regime diagrams, but it was really hard to get good quality measurements to validate those and where those boundaries had been predicted to be. And people had never actually been able to fully observe all those boundaries. And so we tried to set out to measure some of those things and get experimental validation and confirmation. And so if you've ever played with like a Bunsen burner in your chemistry lab, right? It's a tube, fuel comes out, it mixes with air around it. You have a very nice triangle shaped flame. And it's a very thin flame. It's very flat, all right? The air is all moving. So what happens if we introduce some turbulence in the airflow, right? Or in this one, we actually end up premixing inside the tube as well. So we've got turbulence, and it starts being in this picture. And as we start cranking up more and more turbulence in the air, that thin piece of paper flame that's in a triangle starts to get crinkled and wrinkled, and you get all of these wrinkling effects, and it starts to get a little bit thicker and more wrinkling as the turbulent structures enter into that flame front. And eventually it starts making little tears and extinction points. And there's a theory that eventually you got so wrinkled, so torn apart, you could actually just distribute the reactions to a very thick soup of reactions that are just going on in this huge area. But it's something that it's been theorized. No one's ever been able to see it happen. And so we started just turning up the crank, seeing if we could even get up there to this notional distributed reaction zone. And so you can see, again, I did some laser diagnostics of these pictures. I did at the same point in space, we lined up two laser beams. So imagine taking two sheets of paper and you've got to make them directly overlap over a fire. And then we separate them in time so that one beam hits and then a couple hundred nanoseconds later, the other beam hits. But I'm measuring both formaldehyde in blue and the OH in red. And the regions where they overlap is actually the very thin flame front. And so now I can measure the thickness of that flame front, the degree of wrinkling. And this was a really interesting piece too I picked up in research there, was how much cross collaboration there is among fields. And what do I mean by that? Going back to another point I said, we're all visual creatures. A lot of things we do is optical diagnostics. And so computer vision's been a thing for a number of years in different applications. It started, in different manufacturing contexts, seeing like, was a part good enough, reject it or confirm a part as on an assembly line. We use it in autonomous vehicles right now, trying to see, can it detect people coming across the road, right? Facial recognition software, all kinds of different uses. But one of the things that I found as I was trying to analyze these tiny wrinkled structures in this image was a code for some doctors had developed to measure your veins in the back of your eye to detect if you were starting to develop different diseases. And so the vein thickness in your eye could tell them some medical information. But the code, and when you reduce that to just a black and white image, tiny little wrinkled structures. They were the same thing as the tiny little wrinkled structures I saw in the fire. So I could take their code, modify it, use it in measuring my flame fronts. And then I turned around and I modified and I handed off that code to my wife's research, where she was looking at the thickness of different brain structures that are involved in learning and memory. And so we're all using the same set of instructions to analyze thicknesses of different black and white images, but for very different outcomes, right? And so one piece of science that you never imagined could be useful, we posted that code as just a general tool that was used in all kinds of different fields. So after that, I ended up coming and taking a job here at the Army Research Lab. So just a little bit about what that is. You may have heard of us, you may not, but we are the part of the Army. So I'm an employee of the Army that does the fundamental science to really develop the future capabilities that our warfighters are going to need, right? So work with the part of the Army that imagines what would the future look like, help them figure out, what is it that we can't do that we were going to need to do to protect them, right? To enable them to go and do their mission, be successful, and come back home safely. And so we are the scientists here in the lab. It's a little bit different. It's not like, the stereotypical movie image of we're guys in white coats behind a fence, miles back by armed guards. That's not how it is. We are collaborative. We're open. We publish, right? We can share in conferences and journal articles. The research that we do. We work a lot with academia. We work with industry partners. We work with other government laboratories, really tackling after some of these science questions, because there might be hundreds of valid science questions in a field, but only 3 or 4 of them are really the Army science questions that we need to answer to get towards these new capabilities. And certainly a lot of things we do also enable technology to be developed in the civilian world, right? So things you could think back to like the DARPA program that invented the internet. It was originally a military thing to help the academic partners share this sensitive data with each other, but then it turned into a thing we all know and use right now. So the Army Research Lab, we have these competencies. They may be too small to read, sorry, on this image, but they kind of correlate to all the normal fields. We have biology, we have chemistry, physics, material development, information sciences, computer sciences, and all those different problems wrapped together to really get after these technologies. We also have a couple of cross competencies. So as we find more and more technology solutions really need input from a wide variety of fields. And I'll touch a little bit more on the program that I'm working in a second. Also, just the last thing here, right? We are spread out. There are locations across the country. The main facilities are here in Maryland, where I'm located, but we do have locations kind of coast to coast. So my research here at the lab is really looking at trying to link up what is the fuel's chemical makeup, the ingredients in the fuel, and the physical behavior of that and the combustion of that. How does that all come together to produce useful effects, and how can we modulate those and control those to get the kind of capabilities? And one of the reasons we have to look at that is jet fuel properties, right? So there are standards and specifications that kind of control what can be sold as jet fuel. And for your civilian airliner, right, certain properties don't really matter in a jet engine. But if you take and you want to use that in, say, a piston engine, all of a sudden those properties really do start to affect. And so when we have things, the barrel of jet fuel you buy on the East Coast is different than the barrel of jet fuel you buy on the West Coast. It's different than the barrel of jet fuel you might buy, say, in Hawaii. Right? There are different properties based on the local feedstock, the local refinery. There are different variations and tolerances on those. And where they may not matter for a certain aircraft, they start to matter in other applications. And so if we can understand those and how those work, now we can start making our engines more reliable, less likely to break, less likely to stop working. And maybe in the future, we could enable even where we could find fuel locally. We didn't have to bring it all with us, right? So right now, when the DoD goes somewhere, we bring all of our things from home. So if we didn't have to bring as much stuff, that might make us a little bit more robust and reliable. So again, I started doing optical diagnostics, right? Just like I did in my thesis, but branched out to some new and cool things. So if you remember back on that last slide, that big ball of yellow flame, sometimes that flame, depending on the conditions we're looking at, it's so bright that it even overwhelms that reflected laser light. I can't get a powerful enough laser in there to look inside the flame, and my camera is just overwhelmed by that light source. So how do we look inside that? How do I understand flames or how do I understand liquid spray behavior inside of flames? For years, the community had kind of been only able to understand liquid spray breakup if I didn't turn the fire on. I could only do it in a non-reacting sense. So we were one of the first people. We went and partnered with the Department of Energy. They have the Advanced Photon Source in Chicago, which allows you, it's a big synchrotron, which allows you to use X-ray beams. And so instead of using a laser to give me data, I used an X-ray source and then put cameras on it. And that resulted in kind of these data sets here. So I'm looking at how does the fuel break up into ligaments? How do those ligaments break out into droplets? How do they evaporate and then ignite for different conditions? But I'm doing that with the actual reacting, combusting flow boundary conditions. And it's a place that we've never been able to access before. And so I can do things like this video that's playing. So high-speed video, it's a couple 100,000 frames a second. Right? No, this one's only 90,000 frames a second, I think. But you're looking where this yellow arrow is pointing at. It's watching a droplet of fuel, and it's going to kind of go up and then explode into a ring. Well, what interacted with it that may explode? That's actually the spark igniter. So the spark igniter is a plasma, which is why it's kind of invisible in the X-ray realm for this image set. But you can watch then how does these liquid droplets interact with that plasma to really get that moment of ignition when you first turn on our combustor here, right? It's the replica combustor. And so that was a really interesting data set. It told us a lot about these different fuel types and what were their critical properties, and really was able to update the understanding of the field in science about how does being in the hot gases of the reaction zone changing the spray droplet breakup that we thought we had all measured in a cold sense before. So the other video that I've got, so what you're looking at here, I'm going to let it play through and just talk for a minute, but you're looking at a Schlieren imaging. So Schlieren, if you've ever gone outside on a hot day, right, and you look out in the distance over the sidewalk or the road and you see that little heat shimmer, or you might have seen it in like movies of the desert, right, the heat shimmer in the distance. That's the density gradients of that hot air reacting with light waves. And so the cold air and the hot air, that density gradient, wherever they meet, is going to make the light bend. And so we can apply that same principle and make it work for us in this imaging technique. So the different density gradients between the hot atmosphere around the fuel injection and the cold fuel being injected, and then watch as it combusts and watch those density gradients. So let's see if I can get this to play again one more time. What we're looking at here is 3 different kinds of fuel, or 4 different kinds of fuel. So we're looking at the cetane number. So cetane number is kind of the same thing. If you ever pull up to a gas pump, there's different numbers, right? 87, 88, 90. Those are octane numbers for gasoline. They're kind of a measure of how well the fuel will auto-ignite or inhibit autoignition. So octane numbers for gasoline, for similar heavier fuels like diesel fuels, kerosene fuels, there's kind of the inverse of that number, 1 over that roughly, is a cetane number. So how well is this going to run in a piston and compression engine? And so we're looking at we develop some fuels to systematically vary that. And let's see if I can get this to play again. But as that fuel vapor comes in, there's this kind of moment right before the ignition event, right before the big explosion, where it disappears in the background. That's the first stage chemistry. That's the first initial heat releasing reactions to where the density of that vapor turns into the same density as the background. And then there's that moment where it all kind of explodes. And that's the second stage, kind of the power producing part of it. So I can measure both the first stage early chemistry and the second stage chemistry and correlate it to the different ingredients in these fuels. And you can see just visually right here, as I go to lower numbers, it goes further downstream before it ignites. And the kind of shape and quality of this ignition cloud changes, right? And so, clearly this one did not burn as much of it as rapidly as, say, this one. So there's going to be less power in my engine. And so doing those kind of correlation studies, we've really kind of tried to understand and develop more robust engines. And then that led to, as I mentioned before, there are these essential research programs. So cross-cutting multidisciplinary problems that are looking at Army big things we really need to get after. So as there's more and more unmanned systems starting to be in existence, and we want to start using those in different places in the military to take soldiers out of harm's way and add more tasks and more sensors to the battlefield. So there's this need for more power and more power on board them, right? If you go out and you get a small drone from Amazon or whatever right now, the battery pack probably only lasts 20, 30 minutes. And if you take it on a cold day, it probably only lasts 5 minutes, right? But if we imagine, right, in the future, we can't say, pause, time out, I need to go find a charger, right? That's not how operations are going to work. So we're getting after what kind of solutions are there. So building off of the work that I was doing before kind of led into some of these questions about, when I get different fuel properties delivered to me, how can I make that engine reliably produce power? How can we keep it from breaking? Can I have new materials in the engine? Can I have new sensing? Can the engine kind of sense what kind of fuel you dumped into it, adjust itself and keep going? If it gets a bad batch of fuel, can it adjust on the fly? Also, asking the questions about what kind of hybrid electric is right. There's a really interesting trade space between things that are really small, quadcopters and such, that are probably going to work on batteries, and things that are really big, like helicopters or large drones or large vehicles, large ground vehicles, where engines really make more sense than pure batteries. But can I push out to the right by doing advanced hybrid electric? Are there places where I can integrate hybrid technologies to get more performance? And what's the right amount for the right platform, right? The answer for a ground vehicle is different than a flying vehicle. Another challenge in hybridization then is similar to what I learned back in my first research project, right? When I made that big electromagnet, it gets really hot when you push electricity through it. So how do we manage these thermal loads, these extra thermal things that I'm putting into a vehicle? And a lot of systems that get developed, it's good enough for civilian space where I'm on a big, nice formed road. But if I wanted to go drive that in the grass, or I wanted to go fly it, it's too heavy now. So how can we make these things lighter weight? What kind of new materials and designs do we have to come up with? And then the last kind of area of our questions is looking at, if I start deploying teams of these systems, right? I can't have someone whose job is just change out 1,000 batteries for 1,000 drones. So is there a way that they can start sharing energy amongst themselves? Could they start making decisions on Who should go over and scout the left point, who should go scout the right point based on the amount of power we have as a team. So how do I share that energy? What kind of technologies do I need for that space? And who should go do what job? And it's really the traveling salesman program on steroids. So if you're familiar with the traveling salesman program, it's a logistics problem. People like FedEx or Amazon want to solve this problem. They've got fixed warehouses and they've got people that can go out and deliver goods. And that's a really challenging math problem. But then what if my warehouses can move too, right? What if I have multiple warehouses that are all moving and my delivery carriers are all moving? And the math on that, it's multi-variable problem just gets really crazy. And so it's a fun, challenging, basic math problem that we're answering. But at the heart of this, it's all physics problems, chemistry problems, materials designs, control sensing. There are basic science questions that we need to answer to enable these new technologies to be developed and have an impact for the Army. So we'll close out just my part here with the ARL opportunities that exist. There are a number of different summer programs. Kind of year-long programs tend to be more as you enter into undergrad, but you can go to this website that I've listed here. If you just search Army Research Lab and click on careers, you can also navigate your way here, but expand that tree. There are full details on the different opportunities that are going on. And usually kind of time cycles, it tends to be more like a midwinter deadlines to apply to the programs. So for the current summer, it's probably all of them are closed, I think. But keep an eye on that web page and you can read about different opportunities that are available through those programs. But usually we have a good host contingent in the lab every summer or at one of our partners that we work with at one of the universities on one of our funded efforts. And so with that, I'm happy to take any questions you guys have.
Thank you so much for sharing. It was very impressive. And I noticed that a lot of those imaging, to me, of course, they have great scientific purpose, but they also almost look like art pieces as I'm looking at them.
Yeah, we definitely have some of them printed out just to hang. One of the other fun things, so the combustion community, the national meeting has an art competition. So all of us who do in this field, just off to the side of that national meeting, there is an art competition for flame images you've measured in your work.
Talk about cross collaboration and cross curricular activity. All right, we are opening up our Q&A. So if you have any questions, begin dropping them into the Q&A section. I'll go ahead and get it started and just, shout out to all you students out there. Don't be shy. Feel free to ask any question. Starting from the beginning, can you speak on how to choose a research topic and to generate a question? Because I noticed a lot of students want to go for like the overly complicated route when a lot of the times you don't need to reinvent the wheel.
Right. Yeah. So there's a couple good things about that, and there's another slide deck I would grab a slide from. But we've gone in this, and I should also mention, right? There's kind of as you develop science, there's maybe at least two flavors of thought. There may be more, but there tend to be some people who really want to work on the very large problems, and you're going to be working on just advancing knowledge in that area, knowing that someone someday is going to build off your knowledge, will build off your knowledge, will finally solve something. So maybe in an area like fusion, right? You're not going to solve fusion in one day, but you're going to advance human knowledge this tiny increment, and then someone else will increment and increment. And that's really what drives them and gives them passion for their work. And I fell into the other school of thought and it's partly why I ended up at the Army Research Lab as a good fit for me, is because I want to see, answering some very specific guided focused questions to get to a technology answer. And so our method for how we do that is you really start to think about, so imagine that future. What do we really need? And then take a step back and say, why can't I do it today? And if you compare those two images, you're going to figure out you can identify this is the gap, this is the missing information. And then we drill down on that, like ask yourself 5 whys. So why can't I do that today? Well, I don't have this information. Why don't I have that information? Well, what's missing from that? Okay. And you'll drill down to some really core nuggets of good science questions that you need to answer. And then you can start thinking about how you might going around to answer those and build out an experiment for those. But kind of that process of doing your homework for what exists right now, really doing your homework. And then when you're imagining that future, not just your imagination, but actually asking the people who might use your input, right? So if you're going to make the best car for inner city drivers, you better go to talk to inner city drivers and say, what car do you actually need it to be? Or, whatever your product or your thing you're eventually want your science to end up in. So it's a little bit blending of applied science with really foundational fundamental science. And you can bridge that whole gap to really focus ourselves.
Awesome. It's really cool to hear how you can break it down into bite-sized pieces, especially since I think a lot of people view research in a vacuum where it's just
Yep.
isolated in a lab, but really it has a global impact. We got a question in from Cooper. He says, what are some of the major private partners that you work with for your research? So I think that some of that cross-collaboration piece there.
Yeah. So like I said, we work with a number of universities and industry partners. So as I'm in kind of the power and propulsion field, we work with both some of the big people, right? So in the U.S. there are three kind of main engine manufacturers, and we talk to them all the time. We also work with small businesses. There's a lot of, especially from the government side, there's desire to fund small new startups and develop new industrial capability here in the U.S. So there's small business set-asides and grants and programs they can apply to. So a lot of the new and upcoming people and new ideas there too. And it's a good mix of both of those.
Thank you, Cooper, for throwing in that question. And then just chat. If you got them, keep them coming, all right? All right, Xander. He says, do you think or expect that you would end up going into military research lab work? And what were the benefits of going into a government-related job post-college that you've seen?
Yeah, I mean, so it was one of those things as I continued on. I think the idea, as I learned myself, like I said, what drives me, what made me passionate about was having that focus and mission for where my research would go and support. And so explored kind of all the government lab ecosystem. There are other labs at the Department of Energy for my field, right? Department of Energy and Department of Defense, NASA, FAA, all have different research programs. And so I like the idea of having a targeted focus for my research. And then this opportunity at the Army came up, and I was able to join here. But certainly the way I'm wired, that really was a natural fit for me. The benefits, some of the interesting things about the government problems that, say, an industry or a university can't attach is we tend to go after some of the things that are more resource intensive. So things like, I mentioned APS, the DOE facility had those X-rays. Some of those kinds of experimental facilities you can't build without a lot of investment. And so some of the niche areas that aren't really necessarily short-term profitable for a company to build. Some of our engine test cells and things that we have here at the lab, and just one of a kind, right? There's one of my large chambers to study combustion. I think there used to only be about 5 in the world. I think we're up to maybe 10 in the world. And we have one of them here. The government was able to make that investment for the research to get after these hard questions that no one else. And so that was always one of the kind of benefits of being here in the government lab is you've got some really cool equipment to get after some really interesting areas of science.
Just to add into that question, can you describe a little bit like what a government research team might look like, size-wise, interdisciplinary-wise?
It can run the gamut, right? From 1 or 2 scientists up to like the program, that essential research program that I'm helping to lead, we're quite large, right? So cuts across 3 different focus areas with all kinds of different fields helping us. We've got electrical, we've got mechanical engineers, electrical engineers, physicists, material science. We have some computational science, autonomy people. So there are all kinds of mixes and matches. And particularly, we try and leverage as many partners as we can to get towards the answer.
And with that, what skills do you feel are the most useful when it comes to your area of study?
I mean, so a strong grounding in kind of math is always, you're going to use math wherever you're going, sure. But the ability to kind of research and summarize things. So going back to like how do you pick a good science question, you've got to actually know the field. You've got to be curious about and pursue what has been done before, why didn't it work? So being able to kind of synthesize all that data down and find a nugget of what was the usefulness. It's not just about reading and memorizing 1,000 articles, research articles. It's, kind of connecting the dots a little bit. So synthesizing things, curiosity, and then, you've got a little bit of drive or passion for it. So finding the kind of science that speaks to you and makes you want to get back up in the morning. Null results can be disappointing, but then they, like I said, they create a whole new field of questions to go after.
Fire and lasers, right?
Fire and lasers, right? I mean, I got a job where I got to play with lasers and light things on fire, so I can't complain.
Can you talk a little bit more about your experience with RSI and how that might have impacted your professional work?
Yeah, I mean, so RSI, I was a high schooler. I generally kind of knew I liked engineering-ish things, and I kind of liked aerospace-ish things, but I didn't really know what that looked like, what that was. And so going into the lab, getting to do a project, like I said, getting to design experiment, the whole process of you've done a high school physics lab, right, where you kind of do a canned experiment and you write up some data and you have to write a report. And it was, yeah, but doing something where you're actually trying to probe for new understanding, new learning, I knew that was interesting, and I knew that aerospace was interesting to me. I also learned a little bit that space systems maybe weren't as interesting as other things. So some good, some bad, but definitely created I think I wanted to do something research based after that, right? So I didn't just want to do engineering and product design and make something, but engineering research. How great it is if you are able to apply and go for it and get in there. It is a great experience.
Absolutely. I know we have a lot of eager students ready to try out RSI and give it their all. We have another question in the Q&A. It's probably a little difficult to answer, but it's what is your favorite topic that you've researched or favorite project that you've ever done?
So probably somewhere a tie between that stuff that I did for my thesis, just because there was so much new and learning about that, and learning about fuel sprays, learning about jet fuels, learning about lasers and all those things, and got to spend a lot of hours in the lab. So it's good and bad. But then the other project that I've really enjoyed doing some efforts on kind of trying to, how do we miniaturize things, right? So as you try and take any kind of engine and you try and make it smaller, eventually you reach this point where the losses, the heat losses out to the surface area of the volume kind of overcome the amount of power you can make. And so it becomes inefficient. So there's kind of these physical limits to how small you can make things. And so getting creative ways to overcome that has been an interesting research area for, they don't look like your normal engines anymore. And so it's kind of just, how do you get around nature and get yourself into a different regime that will apply.
So a question that I was thinking of was, are there any resources or activities that a student can do to just dip their toe in or get introduced into aerospace engineering?
Depends on kind of what flavor, right? So I guess aerospace, you've got a split between, do you want to be in the atmosphere or out of the atmosphere? And then kind of the aerospace topic fields tend to be structures, how do the things experience and break and not break and bend, controls, how do I keep it flying when things like wind gusts hit me, or fluids, right? How does it interact with the fluid around it? How do we combust things? How do we propel things? And that was the other thing I learned in college too, is I definitely did not want to do controls. And I didn't want to do structures, but fluids worked for me. So it depends on kind of like which avenue you want to pursue. Things like the space side, there's you can try, there's often amateur rocketry societies around, right? I know a lot of hobby groups exist for that, and you can kind of just go and play and see what that is. You'll get experience at different portions of this, and as you try and make your own rocket bigger, you're going to hit research topics fast. Like I said, checking out the university system, you don't have to even do a full internship. If you talk to these professors and you just want to volunteer in the lab, you show you're committed to that. It's often able to just do small unpaid volunteer work. A lot of the professors I know in undergraduate took on people that way. Other things you can do, attending, there's things like this. NASA, I know, puts on different lecture series. You can kind of, it's not really doing an activity, right? You're more receiving information there. I'm trying to think. Other opportunities. Yeah, those are some I could think of right now.
think the Amateur Rocket Club is a great idea. I think that's a really cool opportunity for students to look into.
Yeah.
Let's see. Sean is asking, what is your stance on theoretical and experimental research methods?
Theoretical, probably what you may be meaning to ask is in like simulation and computational. And so, because theory at its heart does support both sides of that, right? But things that are more like just you're solving it on math, you're solving it on a computer versus experimental. And really, when you want to get to the new technology, you've got to do both. There's a limit to how many things I can do in the lab just physically. And there's also some physics limits to how I can, put cameras or put windows or make an instantation of this thing that we're trying to observe. And so there are things that I'm always going to hit up against those limits. And then I bring in the CFD to pair it with me, the computations and the simulations. But the other thing is, from a simulation standpoint, how do I know it's true? Right? Garbage in, garbage out in a computer program. It'll tell you an answer. You have no way of knowing if that answer is real. So how do I validate those systems? How do I, when I make these new simulations and models, what are the assumptions that are cooked into them? How are they validated? And so can I bring in experiments in a known use case and then push the simulation to some place I can't get to? How do I build trust there? So they really work hand in hand. But I'm also very, and there are certain amounts of simulations I do myself, but I'm also primarily focused because I realized what makes me tick was I can go in and turn a wrench. I don't want to sort through computer code and find the missing comma. That I can only do that so many hours a day, but I can go down and fix a broken camera or something quite longer. So they go hand in hand and they both serve great purposes.
You had mentioned about the growing use of machine learning and AI in these industries. Do you feel that AI will be what's going to look for the missing comma, or how is AI in development with that?
Yeah, so that's a very fun philosophical question with a lot of different ways it can go. But right now, what AI does is tends to be basically machine learning. So aggregating a lot of ways that people have done something, like write a paper or do this coding task, looking at a lot of examples and then saying, okay, most often the example is this, and so I can replicate it. So error checking your code, correcting the grammar in your paper, those are things that the current AI models would do a pretty good job at. But generating truly new things, they're prone to making up something that's not real, not feasible. So you can have it write new code for you, but then you always have to go back in and verify, okay, that's not actually a command. Or you can have it write your paper, but it's going to make up a citation that's not real, right? So these are the problems that exist. So AI is great at when you've got a task that you want to automate. Like a place that we used machine learning that was really good was back on those Schlieren images I showed, right? It kind of looks like a big ice cream cone. Well, I need to measure the time history. And that's a task that's really hard to code the computer to do. But if you kind of hand score a couple and then teach the computer what you're doing, because your eye sees the difference between the fuel vapor in the background, but to a computer, they look too similar. Unless you machine learn a number of data sets, and then it can go in and rapidly score. Because the other thing about high-speed imagery is, right, if I'm taking 100,000 frames a second, and I take that over a couple hours of data, I now have millions of frames of images I've got to look at and score. And so if I can machine learn a model to draw the outline of the combustion event for me, that's a great application to accelerate my research. So it's never going to replace the scientist, but it can be a tool to make my job faster.
Thank you for encapsulating about that. I know a lot of the students are really curious about AI and its role in our
Yeah.
future. So for you, what do you think is the next step or the next stage for aerospace engineering?
Aerospace as a whole, where is hypersonics actually going to be able to apply? You know, it's one of those fields that's been ups and downs since I was back in high school, even that we can do niche applications of where is it really going to take off? Can we make this notional hypersonic jet airliner? Is the Concorde derivative going to come back? Is it always just going to be for military uses? The other question is where in space exploration are we going, right? So the argument that keeps going back and forth about should we go to the moon? Should we go to asteroid belt? Should we go to Mars? And there's pros and cons to each of those arguments, so it'll be fun to watch where that goes. But certainly, the idea of we're probably going somewhere. The question is, where should we go next first? So those are going to continue to go. I think it's going to be interesting to look at too how much the general kind of large on-demand satellites is going to impact things. So we've got a lot more of that technology advancing to where you can rapidly deploy small satellites. And what does that enable in terms of communications, telecommunications, and just a variety of applications.
And I hope if any students were listening very closely that they could have some good footholds for some research in the future. If anybody
Yeah,
has any
good.
additional questions, please share your questions with me at rebecca.carter@cee.org, and I can email our speakers in the future. So thank you again to Dr. Temme. It was a fantastic presentation. I learned so much about fire and lasers and everything in between. I would like to thank our sponsors who provide this free and accessible programming to our students, including the Claude Moore Foundation. If you'd like to continue attending these events for free, please make sure to sign up and register for our future sessions and to give us a shout out online. Please mark your attendance by completing the post-webinar survey. And just a shout out, we have another webinar scheduled next week, Study Skills for Success. So we'll talk about study skills and stress management during the testing season. Thank you again to everybody who's joined us today. And finally, fantastic thank you to Dr. Temme.